In the last video, we went over the basic theory of a method by Christian Otto Moore known as the moment area method. In this video, we're going to work some examples. So without further ado, let's get started. Alright, so welcome back. This is part 2 of our moment area method discussion. And so this is one of our geometric methods, and in the last video we talked about the two basic theorems, one where you can find the differences in angles and the other where you can find tangential deviations. In this video we're going to be just working a couple of examples and showing you some twists and some other things that you have to consider as you work the method. Our examples in the last video were very simple just to kind of illustrate the concepts, but now we're going to actually start to apply it to some more interesting structures. So the first one that we have is actually a cantilever beam in which it's simply supported. The cantilever end is at A. Okay, it's supported at B, which is a distance of 6 feet, and then it's simply supported at C with a back span of 18 feet, and we're going to put a point load of 30 kips on the end of this cantilever. All right, and so as you might expect, point A is going to move down to A prime, and then B stays put because it's a boundary condition, and C stays put because it's a boundary condition. And I can draw the M over EI diagram for this if I do my statics, and again, I'm going to assume that you're able to compute the reactions at this point. That we have an upward reaction of 40 kips and a downward reaction of 10 kips, and this is down because the back end is wanting to lift off, so this force needs to hold it down, okay, based off of that 30 kip load out here on the end of the cantilever. All right, and so the moment diagram, so this is the M over EI diagram is here, okay, is a minus 180 over EI, and it's kind of this triangular shape over the entire length. On this, again, I haven't drawn the shear diagram just for the sake of these are being simple enough that I don't need to do that, but in practice you probably should. Okay. All right, so let's take a look at the construction using the methods that we know. Now, if you recall from the last video, we said the entire process is all about drawing the tangent line. So in this particular beam, what we are after is theta A, okay, and finding the deflection and the slope at A, as well as the deflection, well, the deflection, but the slope at C are all things that we want to kind of look at. And so this is my tangent line construction process. And so there's kind of a puzzle to solving this and figuring out what it is that you can figure out. Okay, and so the methods that we have here is that let's just, for the sake of this discussion, let's start and try to find theta C first. Okay, and because it's kind of the most familiar to what we've been doing with the basic tangent line construction. So we're going to take the tangent at C as my starting point here, because I need to know theta C, so this has to be one of the points. Okay, the other one you have to look at is, well, what are the other two places other place that I should choose as my point? And if you look, if I go out to the end, okay, and I draw my tangent lines on this, the tangent at A was clear out here, right? It's A has dropped down and it's rotated counterclockwise, and so the tangential deviation at A with respect to the tangent line at C, the C was this line that took off up here. So then the tangential deviation goes from here all the way up to there. Okay, and so, well, okay, I can calculate it, but the problem is that there's an unknown amount here in this that is caused by the rotation at y, or not y, sorry, this arbitrary distance y, okay, and then we know that our definition of A to A prime is delta A, so then this tangential deviation between A and C is equal to whatever this distance y is, okay, plus delta A is going to be that tangential deviation value. Again, I can calculate this. I don't know either one of these yet. Okay, so let's go see if there's some place that might make a little bit more sense. Okay, so the only other point on this particular picture is B. Okay, and so if I were to draw the tangent line at B, it's the line that kind of comes in and does something kind of like that. And again, it's it's actually probably a little flatter. My curve isn't continuous, but you guys get the idea. It's kind of doing this. All right, and so that tangent line, and because this is a support condition, that tangent line goes through the support on this, and so then if I look at this tangent, well, this is the tangent to C, and this is my tangent at B, this becomes the tangential deviation at B with respect to C. And that's a pretty useful value, right? Because I got rid of this extra unknown that we had when we went at A. Okay, so that's one of the things that we look for, is we look to try to set these tangential deviations up, usually by drawing them through supports for at least one of the points as a reference. Okay, because at the very least what I can do is now I can start looking for triangles that I can work with. And if you look, here's my theta C, and I see a triangle that goes from C to here and down. Okay, and we know then that I can set up a relationship that says that, okay, well, the tangent at theta C is the tangential deviation BC divided by that length 18 feet. Okay, or an equation that looks like this. Now, realistically what's happened is that there's also a tangent in front of this, but if you remember in our theorem, we said we were looking at small displacements, and when that happens, the tangent of theta is the same as theta, so I don't need that tangential marker here. So the theta C is basically, and I'll say approximately, TBC over 18. Okay, and then we know how to calculate this. So if I can calculate TBC, then I can get theta C in one shot. So the formula, we said, the second theorem was the tangential deviation between 2 points is the area under the M over EI diagram between those 2 points multiplied by x bar to the point that I'm interested in. So we want the tangential deviation at B, so I need the x bar B for all of this in order to be able to figure out the difference of the tangential deviation. Okay, so the area is the area between B and C on our M over EI diagram. So if we go back and we look at this guy, that's just going from here to here. It's just a simple triangle, just like what we did before. And so minus 180 over EI, okay, times a half times 18 feet will get me that area. And then the centroid from, if that point is here, again, we're completely neglecting that side of it because I only need between B and C according to the theorem. Okay, then this becomes the x bar that we're looking for. And if that's 18 feet, then this is 1/3 of that span because it's 1/3 of the length to the high end for a triangle. Okay, and so that ends up only being 6 feet. Okay, all right. So if we go through and we look at doing our calculation, we can see that this is a half times 18 feet times minus 180 over EI. That was the area between B and C, and then 18 over 3 is the centroid. And I do my math on this. This is minus 9,720 over EI. Now again, you've got to kind of be careful on the units. There's a foot, and a foot in this. So if I want to calculate this, you know, then if the actual calculated numerical value, you've got to kind of watch the units. Now we're just doing it symbolically, but you still got to be kind of mindful that there's kind of a kip feet squared kind of thing riding around on this, or I guess kip feet squared implied in this top value. Okay, so then if that's TBC, then all I do is I take this value and I divide it by 18, and I now have the angle that I'm after. All right, and so the math on this is minus 540 over EI, and again, the numerator of this thing is kip feet squared, and then you have kind of a kip inch squared thing in the bottom. So if you were to plug in the values, you'd have to make that units conversion. Okay, now again, it's a minus because of the minus on the moment that's on here, so that implies that our angle is going to be a minus. And if you look at what happened in our picture, it went from here originally to here, which is a clockwise rotation, and that clockwise rotation then is a negative indeed, and so this starts to work out for us. So we're in good shape on that one. All right, so now let's go in and see what we can figure out next. Okay, so now I have theta C, and I also have tangent at BC, and I can calculate this guy. All right, well, if you have one of them, I can use the fact that I know that this is a tangent line at C and this is my tangent line at A. I can now use the change in angle theorem, the first theorem, to calculate the change in angle for theta A. Okay, and so this is going to be then, the change in angle is going to be theta C minus theta A is going to be what we have happening here. Okay, all right, so that's what we're going to do. So we're going to calculate this change in the change in angle. So the change in angle then is theta A minus theta C. So you take the angle of where I'm at minus the angle of the reference, and that should get me to my equation. So I can do a little bit of rearranging here and say then, well, then theta A is equal to theta C plus that change in angle. So we got theta C from before, and I can calculate this quantity. I can find theta A. So let's do it real quick. The change in angle between A and C is the area between A and C. This one's, there's no moment arm on this one. It's just the area. So this is 1/2 of 24 feet times a 180 over EI on this thing. And so my angle, change in angle on this ends up being a 2160 EI for us on this particular case. All right, so then if I plug that in, okay, we can come in and we can now calculate theta A. And now what I've done here is, again, this is, we're kind of doing a kind of a magnitude kind of operator on this thing. And so you can see that, well, what happened to the minus sign? Well, again, we're just kind of looking at the difference. And this is where drawing the pictures helps. All right, that this theta AC is going to be theta, the magnitude of theta A plus the magnitude of theta C. And that will kind of help you with some of the sign convention issues to calculate this guy. Okay, so that's kind of what I've done on this, is that I can say, all right, well then if my theta C was a negative 540 EI and the total is 2160 on this, then that should leave me with 1620 here. Sorry, I was a little bit low on the paper. So here's the minus 540 over EI, here's the 2160, so that gives me 1620 EI is my theta A value. That's the equation. And again, this guy is positive because we would expect it went from here and it ended up here. That's a counterclockwise rotation. That is positive. So the trick in all this is you got to kind of watch the signs and kind of apply the signs in order to, so that it makes sense. But I know that on the picture, again, from here to here was theta C, and from here to here was theta A, and the magnitude of those two guys together should be the same as the magnitude of that. And so you can kind of manually assign the signs to be able to account for that. So that's theta A. Okay, the next piece then is, well, how do I get delta A? Okay, and so we're looking at, well, what can I calculate that has this guy in it? And so we'll come back and we'll look at this tangential deviation. So it's the tangential deviation at A with respect to C. It went from here to here. And we know that it's the sum of this Y plus delta A calculation. Okay, the problem is what is Y? Well, again, if we look for triangles, if you look, we had a triangle here in which I had TBC that got me this height and a length of 18 feet. Well, if this tangent line is a straight line, then that's the same triangle ratio as from here to here over the entire feet. I can use the method of proportions to find Y. Okay, now the basic equation that we're writing in this is that delta A plus Y is that tangential deviation. So if I rearrange, delta A then is tangential deviation minus Y. Okay, so we can calculate TAC as being the area of AC times X bar going back to A. Okay, now what I've done is I've set this thing up so that into two pieces. If we go back and look at our moment area diagram on here, we've basically split this guy. So if I look at the left piece of this, I need this distance. So that's the first distance. So that will be 2/3 of 6 feet. And then the area is 1/2 of 6 times minus 180 gives me that area. And then the other one, the centroid, is going to be here. But now we need that distance, okay, that comes from this point and goes all the way over here. That's the X bar A for the second area. And so that's going to be 6 feet plus 1/3 of 18, or another 6 feet. That should be a 12-foot dimension. And you'll see that in the calculations. And then the area is the exact same as what we did before. All right, so let's go through and let's look at how we can calculate that. So let's look at the math. All right, so here's the first one, 1/2 of minus 180 over EI. Here's the length, 6 feet, and here's the moment arm, 2/3 of 6. Okay, plus 1/2 of minus 180 over EI times 18 feet. So now we're on the BC span. And so then it's 6 feet plus 1/3 of 18. So that's the 12 feet that I was talking about. And if you do the math on that, this is minus 21,600 over EI, gets me the TAB. Now, so that gets me, or sorry, TAC. The TAC is this guy. I want this. I still need this guy. But we know that from the triangle that we constructed that this Y is the same thing as 24 times theta C. And so if I take advantage of that, then Y we can calculate as, since we have theta C from before, it's 24 times minus 540 over EI is a minus 12,960. And so then delta A then is going to be my TAC value of minus 21,600 minus Y. And so it's minus a minus, or plus 12,960 over EI. So my delta A is now minus 8,640 over EI. Okay, and so this tells me, the minus sign on that tells me my deflection is downward, which is kind of what I would expect on this particular problem. Okay, and so that's how we do it. And that's all there is to handling these. So this one's a little bit trickier in that you have some intermediate steps that you had to calculate. We had to find theta c to be able to get to y to be able to get to delta a. So there's some other little tricks that have to happen, but it's all about drawing these lines and these tangential deviations. So I have a vertical, a vertical line here as my reference between a and a prime, and another one for b, and it's just a matter of finding triangles that have stuff that you can solve for. Again, if you can find a TAC, you can always find an angle that that line makes with the horizontal, and that's often a common trick that we're looking at being able to do. All right, so that's how you can handle a little bit more complex of a problem. All right, now let's go to the next level. Okay, and I have another problem. Okay, all right, so if we look at this, what we have is we have now a beam with a hinge. In this case, okay, it's fixed at A, a hinge at B that's 9 feet away, and then it's simply supported between B and C with 2 point loads of 12 kips on it. Okay, so the dimensions are 9 feet, 6 feet, 6 feet, 6 feet. So these loads are centered. And so if I draw the moment diagram on this, M over EI is constant for the whole length. You get a diagram that looks something kind of like this. It's minus 108 over EI here. Okay, and then now this is my hinge location, and that hinge is going to be a bit of a problem, especially when it comes to trying to draw the deflected shape. Okay, and then the simple supported span is this guy, in which it's 72 over EI as the value of the moment at 6 feet and 6 feet for that. Okay, we want to find then the the deflection at B. We want to find the angle at E, okay, which will be the angle at the other side. And then we want to find the angle to the left of the hinge and the angle to the right. Okay, so this is one of those, remember the theorem said that the elastic curve had to be continuous. Okay, and it is a continuous function, but it changes slope. And so we've got to be a little bit mindful of this guy, all right, and that what happens is to the left of B, my tangent line looks something kind of like that, and to the right of B, my tangent line looks something like that. Those two lines are no longer the same line. Okay, and so there's actually a rotation of the hinge that occurs between those. Okay, and that's what causes that disjoint, or the break, if you will. That little, it changes the angle instantly at that location, and that's going to affect the rest of the beam and how it performs. So we got to be kind of careful. So the slope is discontinuous at the hinge. That's the big thing to take away from this. Well, how do we do it? Okay, so the thing that we're going to have to look at is we have to build constructions that allow us to work one side relative to the other. Okay, and so what I'm going to do is we're going to draw our tangent lines. Okay, and I'm going to kind of work all three of them, but let's start with the AB side first. Okay, because I can find delta B, the deflection B, and then moving down to B prime, if that's B prime there. Okay, and this one we've worked. This is that cantilever beam problem that we did before. Okay, that the delta B from as B goes to B prime is the same as the tangential deviation between the tangent at B left relative to A. Okay, and so if it's this line on the left side and this line on the right. Okay, I can't take the one on the right side because I have that discontinuity in the joint. I have to keep everything on the same member. So we're going to take this theta, we're going to play with the tangent on the left and this, and I have everything there because I have the moment diagram over that shape. And so we can find delta B, okay, and that's just simply the tangential deviation at B with respect to A. Okay, and so if we do that, let's do our calculation then. So this is the area between A and B, and this time we're looking for the tangential deviation of x bar B, so we're going to B at that location. And if we look at our moment diagram that we have here, it's just simply this area multiplied by its moment arm. So it's 1/2 of minus 108 times 9 feet, and then multiplied by 6 feet on that, and that's everything that you see here. All right, so here's the area, 1/2 minus 108 over EI times 9, that's the area, and then the moment arm to location B is 6 feet. This value is minus 2,916 over EI, and that's the displacement at B. So it's kind of interesting if you look at it, the displacement at point B is controlled only by this beam here, okay, by this span. This span has nothing to do with the displacement at B. Okay, it's just the flexing of what's happening in this guy that we've got to kind of worry about. Okay, but those moments are induced by the point load up here. Okay, all right, so let's take a look and let's go see what we can do about finding theta BL. Okay, this one's pretty easy because we know that theta A is 0. That was my deflection or my slope at A, and since it's a fixed support, it's a 0 value, and so theta A plus the change in angle AB. Okay, so this is a formula that I can calculate. It's just the area between A and B. So that's 1/2 of 9 times minus 108 over EI is minus 486 over EI. So we've got that value. That's the angle at the left. Okay, and now we can come back and we can kind of look at our construction and figure out, well, what can I do with that? Okay, so we've got our delta B. Okay, and then now if I look at the right side piece to the right of the hinge, I now have a tangent, and this is almost a B on the right side, a BR value, that now I start looking at, well, okay, I've got my tangent line that came down for the B on the right. I have my tangent line at E here. Well, that's a tangential deviation, right? And then I know that from B to B prime was the delta B that we just calculated. So now all of a sudden I've got the triangle that I need to be able to find theta E. Okay, so we're going to calculate the tangential deviation from B to E on the right side. And we're going to add to it our delta B, and then we're going to divide it by that length based off of our formula. Okay, and so we can write an expression for theta E that is TBE minus delta B over 18 feet. Okay, it's going to be the area between B and E to times the moment arm that is going, and again, we're looking for the moment arm for at B because that's where this guy is. All right, so when we come and we look, we need to figure out the centroids of these areas. And then the distance, the X bar distance, is the one that goes to here. Okay, now what I did is I've split this up into, if you look at the shape, I've split it into, here's my two triangles and here's my rectangle, and then my centroids are a lot easier than trying to deal with this. Now, this is a regular trapezoid. I know the center is in the middle of it. I could do that, but what happens if these loads are off center? So I'm going to work it the other way as a more generic approach. All right, so let's take a look at what we've got. So the magnitude of the moment is 72 on that. Okay, and so that's a positive value, 72 over EI, 1/2 times 6 is that triangle area. And for the first piece, the distance from here to here, it's 2/3 of that distance, so that's 2/3 of 6. So that's the 4 that you see here. And then I've got 6 times 72 is the moment in the middle. And then it's 6 plus 1/2 of 6 because that's the 9. And then plus 1/2 of 6 times 72. And so now we're going 12 plus 1/3 of 6 is 14. So that's the distance from here over to A. So it's 6 to here, 6 more, and then 1/3 of 6 here. That's the 14 that you're seeing in that calculation. And so the angle for the tangential deviation on this is 7,776 over EI. Okay, and then we're going to subtract off my displacement of minus 2,916 over EI. Okay, and then I'm going to divide all of this is going to get divided by 18 feet here. Okay. All right, so I left off the 18 here, but if I do that, that should get me 594 as my theta value. So here's the delta A, here's that's our tangential deviation. Here's our delta B. Okay, and then we divide that by 18 feet, gets me 594 over EI. And again, this is a positive value. So what's happening is that if we started out here and we're rotating to here, that's counterclockwise. That is indeed a positive value. Okay, so it makes sense to us for what we're doing there. Okay, now if you want to look at finding theta BR, then it's just the same game that we played before. That I can find theta BR as being theta E minus the change in angle between B and E. Okay, so this was the theta E that we found, 594, and then the change in angle is simply minus all of that area. So it should be our change in angle theorem here. And if I do that, the math is minus 270 over EI. And so the theta BR is minus 270. Now, the thing that's kind of cool is you could actually go in and figure out how much that hinge rotated on this one by taking theta BL. So we could do a formula like the theta at the hinge is going to be theta B to the left minus theta B to the right, and the difference that it's happening in those. and that can give you kind of a sense of the magnitude. And this is a useful value for if you're designing like a splice connection in a beam or something, in a steel beam with a bunch of bolts, trying to figure out how much rotation I'm expecting at the location where I'm putting that. That can have its uses sometimes, but you've got everything that you need to know. So that was our second example on this. So I hope this all made sense to you. A couple of more advanced tricks and techniques for some more complex problems. The last one's about as complex as I would go with the moment area method, just because point loads is about all this method is capable of handling. Otherwise, the geometry calculations become a little bit rough. So again, I hope that made sense to you. If you've got any questions, go back and watch the first video. That kind of sets up the theory. This is more just kind of a practical, here are the calculations and some more examples to kind of look at some of the other tricks that are in there. So what were the tricks that we saw? The tricks were, first one is, well, how do you handle the hinge? Again, so we're working the left side, we're working the right side, and we're using the displacement as being the constant between the two. I can't do an angle from A to C because of the break in the hinge, but I can use that guy to back into being able to find an angle and then continue on. So once I have theta E, then I'm in business. Okay, and then the other one was on our example here, was being able to write up our equations for tangential deviation, something I know, into something that I want and something unknown, and then finding that from an alternate source. Those are kind of the basic trick ideas that I wanted you to pull out of this video. So I hope this helps. I hope it makes sense. As always, if you've got any questions, leave us some feedback down below. Toss us some comments, and if you found the video to be helpful at all, toss us a like, and be sure to subscribe to the channel. And we will see you guys next time. Happy engineering.